Flooding causes billions of dollars worth of damages per year, 4 billion alone in the US annually. For low-income communities, such a loss can be disastrous since they can't afford the cost of flood insurance and protection, or for damage restoration. As a result, a single flooding event can create a long-lasting financial burden. Unfortunately, the effects of flooding have become more severe in the recent decades as places become increasingly urbanized and more natural land is replaced with roads, sidewalks, and parking lots, all made from materials such as concrete and asphalt. These materials are mostly impermeable, meaning that they prevent water from being absorbed into the ground. A question now presents itself. Why can some materials absorb large amounts of water while others can absorb almost none? The answer to this question is because they have different water absorption capacities, or WAC, which is based on the properties of the material. One of the most important properties is porosity, the percentage of empty spaces, also known as pores, in a material. These pores hold the water that enters the material. However, it is important to note that porosity alone does not completely determine the water that actually gets absorbed. Two materials may have the same percentage of empty space, and yet one may absorb more water than the other. For example, if a material has many open and connected pores, water can easily travel through the material and fill the pores. On the other hand, if the pores are closed off or not connected, water cannot enter them easily, and so they contribute little to absorption. Similarly, large pores can allow water to enter easily, but may also allow it to drain out just as easily, while smaller pores retain the water more effectively. Therefore, the absorption of water is not only dependent on the empty space available to hold water, but also how the empty space is organized. To compare these materials fairly, a simple controlled experiment can be done to test different materials under the same conditions and measure the water absorption capacity and cost efficiency for different materials. For this experiment, we will be using the following materials that can commonly be found at home, at school, or by going to a nearby supermarket. First up, we have a 266 milliliter plastic cup. It can be any cup, but for this experiment, we will use a 266 milliliter plastic cup. Second, we will get a paper cup that can hold a larger volume than 266 milliliters. Like before, it can be any cup, but this time the cup must hold a greater volume than the previous one. Third, we need water. The amount will vary depending on materials and cup size, but for this experiment, we will only need to use about 1 gallon at most. Fourth, we need a digital scale. We will use this to measure the mass of our material in grams. Now finally, we will need the materials that we are going to test. For this experiment, we will be using soil, aquarium gravel, aquarium sand, paper towels, and cardboard because they are all common and easy to find materials. However, any materials can be tested in this experiment. Now that we have all our materials, we will begin the experiment. First, fill the plastic cup completely with the testing material so that the volume stays constant for all materials. I'm going to start with soil. Once you fill the cup with the soil, weigh it on the digital scale and write down the mass. Then, move the soil onto the paper cup and make sure that the total volume of the material in the cup stays the same. When you are finished moving the soil over, pour water into the paper cup until the water surface reaches the same height as the rim of the paper cup. Give the soil about 1 minute to absorb the water. This time should stay consistent for all other materials. After a minute has passed, drain the excess water by pouring it out until the surface of the water and the soil are at the same height. Now measure the new mass of the soil and water together by placing the cup on the digital scale. Make sure to write down the new mass. Continue to repeat the experiment for each of the testing materials. Remember, the initial volume, not mass, should remain the same for all materials. The final volume of the testing materials should also remain the same. Now that we have finished the experimental section, it is time to calculate how efficiently each material absorbs the water. We will use the following formula. M wet minus M dry all over M dry equals WAC, or water absorption capacity. M wet is the mass of the material with water, which we had measured at the end of each experimental trial. M dry is the mass of the material without water, which we had measured at the start of each experimental trial. The water absorption capacity will be a numerical value between the range of 0 to 1, with higher values meaning that the material is more efficient at absorbing water. Next, we will solve for the cost of the material per kilogram of water absorbed. You can do a bit of research to find the cost for a kilogram of material. Once you have found the cost per kilogram, use the following equation. cost per kilogram over WAC. Cost per kilogram is the cost for a kilogram of the given material in units of dollars per kilogram, and WAC is kilograms of water absorbed per kilogram of material. Dividing the former by the latter gives the cost per kilogram of water absorbed to find the best material to absorb water for the cost. Now that you have finished the experimental procedure and calculations, your data should look something like this. I put my data into a bar chart to make it easier to understand, but a data table is perfectly fine too. As you can see, cardboard had the highest water absorption capacity to cost ratio, followed by soil being the best organic material that we tested. The aquarium sand and gravel ended up being the least absorbent, and paper towels, although having the highest water absorption capacity among the materials, also had the second highest cost, meaning that it was one of the least efficient materials. Even though the experiment showed that the paper towels and cardboard are best at absorbing water, the experiment also found that they physically deformed and became much weaker afterwards. This is especially important because flood prevention materials must be capable of maintaining a good condition over many years, rather than failing after a single storm. Having a material that can absorb water exceptionally well but breaks down easily would be very ineffective, as it would need to be replaced repeatedly, requiring high maintenance and much expense over time. As a result, our experiment shows that soil is the most effective at absorbing water after taking into account water absorption capacity, cost, and durability. This might explain the usage of mud in building houses in some places around the world, but we were unable to test and compare soil to concrete, asphalt, bricks, wood, or many other common construction materials, since we don't commonly have access to it. Regardless, soil still has a very high water absorption capacity at around 0.76, which should show its effectiveness even without other materials to compare it to. Although our experiment showed some results in finding good ground materials to reduce flood damages, it still left many stones unturned that could be expanded on in future experiments. First of all, there are many materials that we have not tested or used yet, such as concrete or wood. Materials such as compacted garbage could even be tested in the future, since it was the foundation for part of New York City. But besides opportunities for future research, our current results can already be applied to the real world. Our experiment found that among the materials we tested, soil was the most practical due to cost, durability, and efficiency. Since soil can easily absorb large amounts of water, keeping large natural areas around urban places would help manage rain and flood water, limiting the amount that could collect on streets. One way we could do this is to create more parks. Parks have many purposes that help citizens, including for physical and mental health, as well as environmental benefits, like having plants to provide fresh air, as well as absorbing water to help alleviate the amount of water that collects in the streets. This will reduce floods and damages. By including parks and other natural spaces in city planning, communities can reduce flood damages before it happens, making neighborhoods and life safer and more affordable.